Welcome to qnawire.
In this question, we are given that we want the electron's wavelength to be about 1 nanometer in order to probe the structure of some crystals. Now, in order to have the wavelength to be about 1 nanometer, there is some amount of momentum we will need, right, based on the de Broglie's wavelength formula, right, where the wavelength is equals to h over the momentum. So the momentum required is h over the wavelength. Now, of course, we don't want to find the momentum, we want to find the velocity, right, which should tell us whether it's relativistic or not. So to find velocity, we just divide by the mass. So we need to divide further by the mass of the electron. And this should give us about 7.27 times 10 to the power 5 meters per second. Now compared to the speed of light, which is 3 times 10 to the power 8, right, this is approximately 0.2% of the speed of light, so it is much smaller than c, therefore it is non-relativistic. We can ignore relativistic effects. Right, now to find the potential, accelerating potential needed, we want to use the kinetic energy and equate this to the charge of the electron multiplied by the potential. Right, so this is the accelerating potential. Kinetic energy can be found by taking half mv square, where we use the velocity over here as the v. Then we just have to divide this by the charge of the electron. And the accelerating potential, we should get about 1.51 volts. Now, of course, to find the kinetic energy for this, just be E times the accelerating potential, which is 1.51 eV. Comparing it with the potential energy for our typical NaCl molecule, right, the potential energy is 6 eV, and this energy over here is about 1/4 that of 6 MeV, sorry, 6 eV, quarter of this potential energy, and therefore it is not likely to damage the molecule, and wouldn't be as very damaging, right, since it is much lower than the potential energy. So it cannot kind of ionize the molecules, right. Now for the next part, if we want to use photons at the same resolution, it means that we want our photons to have the same wavelength of 1 nanometer. What would be the energy, right, of this photon? Right, we use E equals to hc over lambda. So hc will be 1240 eV dot nanometers divided by this 1 nanometer. This will be 1240 eV, right, and this is much more higher than the potential energy of the crystal or the molecule, which means that it will cause damage. It can be damaging because it can ionize the molecules inside the crystals, and as a result cause damage to the crystal. Right, so electrons are actually more favorable in this case to probe the structure without damaging the original structure.